So, welcome back to yet another module of Unit 4, Sensation and Perception. This is a bit of a departure from um, a lot of what we've been talking about. We're going to be discussing hearing, moving away from vision. And the next module will cover the other senses other than vision and hearing. So this is module 20 for hearing. And there are three learning targets that we want to make sure we focus on for this particular module. You should be able to describe the characteristics of air pressure waves that we hear as sound, explain how the ear transforms sound energy into our neural messages. So how the ear takes the sensory information in from the environment and transforms it into what we perceive in our neural messages. You should be able to understand a bit about loudness, pitch, and the location of sounds. And again, I apologize, my two dogs are in the background, moving around a lot. So what is audition? It's just basically, it makes me think of the movie that my kids love. I think it's called Auditions, maybe? And no, it's called Sing. The song is called Auditions. So, sorry about the dog barking. I was saying Audition is the song, I believe it's called Auditions within the Sing movie, which was one that was one of my kids' favorite movies a couple years ago. But in terms of psychology, audition means just generally the sense or act of hearing. And this is a good visual of your ear and the components of what's going on inside of your ear. Your outer ear, middle ear, and inner ear are the three groups that we're going to be discussing. Three parts of your ear that we're going to be discussing. So how do air pressure waves become sound? So draw a bow across a violin, a bow and arrow, and you will unleash the energy of sound waves. Air molecules, each bumping into the next, create waves of compressed and expanded air. Like if you think about the ripples on a pond circling out from a tossed stone. I was just doing this yesterday in a lake, actually, throwing with my two sons, throwing rocks into a lake and watching the circling motion out from the stone as we tossed it. As we swim in our ocean of moving air molecules, our ears detect these brief air pressure changes. So what are the characteristics of sound waves? We have frequency and amplitude. Frequency, also known as wavelength, you can have short wavelengths, which equals high frequency, and high-pitched sound, or long wavelength, which equals low frequency, low-pitched sound. We also have amplitude, which is the height of the sound waves. Great amplitude, those really, really loud sounds, or small amplitudes, really small, soft sounds. So what information do sound waves give to us? What pitch am I hearing? Short wavelengths equals high frequency. Again, high-pitched sounds, long wavelengths equal low frequency, and you have low-pitched sounds. How loud is the sound that I'm hearing? Again, great amplitude, loud sounds. Small amplitude, soft sounds. So, would you expect long or short wavelengths when a soprano sings in an aria? So based on the information we just went over on the last two slides, you should know that we'll go back and look at them. So high frequency, high pitched sounds are shorter as compared to the baritone, which would be longer. So a little bit of an exam tip if you're going to be taking the AP exam, that both light and sound travel in waves. We just talked about vision a couple modules ago. In each case, the amplitude and length of the waves are important to understand. So understanding that both light and sound travel in waves into our sensory systems, and then understanding a little bit about the amplitude and length of the waves is important. So what are the three divisions of the ear? I mentioned them earlier. The outer ear, the middle ear, and the inner ear. So the ear is divided into these three sections. So if we think about sound and how it comes into our ear, this is a really good visual. You can see the blue markings showing the sound waves coming into our ear. They pass through accessory structures to our sensory receptors. The vibrating air triggers nerve impulses that the brain decodes as sounds. The auditory canal, you can see it right there, pointed out like sort of to the left right there, is the channel located in the outer ear that funnels sound waves from the pinna to the tympanic membrane, which is also known as the eardrum. The eardrum is the thin layer of tissue that vibrates in response to the sound waves. So when you ever hear people say, oh my gosh, you're gonna blow your eardrum if you listen to it like that, that's what they're talking about. They're talking about your tympanic membrane, which is a layer of tissue that vibrates when you hear a sound. So what are ossicles? Ossicles made up of the 3 smallest bones in the human body. Interesting little fact there. The incus, the malleus, and the stapes, which you may have heard of termed otherwise. They're sometimes called the hammer, the anvil, and the stirrup. These 3 tiny little bones transfer sound wave vibrations from the tympanic membrane to the oval window of the cochlea. So you can see the oval window right there, and then you can see the cochlea. It kind of looks like a little snail right there. So what is the oval window? It's the membrane covered opening of the cochlea. It vibrates when it receives the sound waves and causes the fluid inside the cochlea to move. So the cochlea is a coiled, bony, fluid-filled tube. So there's fluid inside of it, inside your inner ear. Sound waves travel through it, and the fluid triggers your nerve impulses. Super fascinating stuff there. What would you answer? When you listen to music, the sound waves cause your what to vibrate first? So we talked about that. It would be your eardrum, your tympanic membrane would be vibrating first. So you may notice that some sensory structures are referred to in more than one way, either through, if you're following along with the Myers text or just listening to me. The Latin designation is important to know, but just remember in this instance, the tympanic membrane is what we usually call the eardrum. That's the popular name for it. Make sure you understand both of them because they could be referred to either or on the AP exam. How does the sound wave move through the inner ear? So accessory structures move the sound wave to the sense receptors in the inner ear, where the wave undergoes transduction. Remember that term of transduction we talked about in a couple modules ago in terms of vision, to neural energy that the brain can then process and interpret. The motion of the sound vibration against that oval window right there of the cochlea causes ripples in the basilar membrane right here, bending there, all these little tiny little hair cells that are lining its surface. The hair cells, also known as cilia, movements in turn trigger impulses in the nerve cells, whose axons converge to form the auditory nerve. So think about what we learned about the axons when we were talking about neurons. So these hair cell movements are what trigger impulses in your nerves, and then the axons converge to form the auditory nerve. The auditory nerve carries the neural messages to your thalamus and then on to your auditory cortex. So you can see where the visual cortex is as compared to your auditory cortex. Kind of easy to remember. The auditory cortex is kind of near your ear. Visual cortex, I always think about the example of like if you fall really hard on the back of your head, if you've ever done that, that's when you see stars because that's, you're going to hitting more directly on your visual cortex. So the auditory nerve carries the neural messages to your thalamus and then on to the auditory cortex in your brain's temporal lobes on both sides. So exam tip, pay attention to how many pages, if you have the Myers textbook, are devoted to each of the senses. So one thing you may have noticed is there's more on the eye than there's more on vision than on hearing, and there's more on vision and hearing than on the other senses. So you should be focusing more on, especially vision, and somewhat on hearing, less so on the other senses in terms of studying. What are 2 types of hearing loss? Sensory neural and conduction. So sensory neural hearing loss is damage to the cochlea's hair cell receptors or the auditory nerve. With auditory nerve damage, people may hear sound but have trouble discerning what people say. And you may know someone like that. You may be someone like that. And that if that is what that person is experiencing, that is called sensory neural hearing loss. On the other side is conduction, damage to the mechanical system of some sort. The eardrum and the middle ear bones that conduct sound waves to the cochlea can cause conduction hearing loss. It's less common than sensorineural hearing loss though. So how much sound is too much sound? It might be less than you think, especially in today's world, especially with all of us listening to headphones so much and having the volume turned up way too loud. It can be really problematic. As a general rule, any noise we cannot talk over, whether that's machinery that's really loud, fans screaming at a sporting event, music blasting at maximum volume, it may be harmful to you. And the more you do it, the more often you listen to that type of sound, the more likely you are to have significant damage to your hearing. So it's really scary. So this kind of shows you right here your sort of threshold of hearing, kind of where you can actually perceive something. For most people, it's fairly similar, but not everyone. This would be where a whisper would be a normal conversation if you're on a busy corner of a street in a city or town. And then we start getting into stuff that can be pretty damaging, can actually, create hearing loss. The subway, jet planes, of course, thunder, and all the way up here at the top would be going to like a musical concert and it's really close range. Doing that really often can have significant long-term damage to your ears, to your hearing. So what's the problem with headphones? Well, with headphones, if you're listening to music or listening to something, even if it's a podcast or something, and you just like to listen to it really, really loud, headphones direct all of the sound waves directly into your auditory canal, and they bombard that basilar membrane. In the open air, sound waves have the opportunity to disperse and are not all directed in one location. So it can be really problematic, more problematic if you're listening to, really loud sounds with headphones when it's being directly bombarded into your basilar membrane. So, but headphones can also be helpful, right? So this is a cute little picture of quarterback Drew Brees celebrating in 2010. And he knew that it was going to be crazy loud and amid the pandemonium of the celebrations. And he had earmuffs, headphones to noise canceling headphones to protect the vulnerable hair cells of his son. So the noise canceling headphones could be a great strategy to use if you're going somewhere where you know it's going to be really, really loud, so you can protect your hearing. So what about the research on hearing loss? Since the early 1990s, teen hearing loss has risen by a third and now affects 1 in 5 teens, which is sort of crazy. And we have to think about the different things that we're doing in our society that are probably causing that. And it is probably us listening to headphones, wearing headphones a lot, listening to music, or not just music, just the way learning things. Like I said, doesn't have to be music, just listening to things at a loud volume. After 3 hours of a rock concert averaging 99 decibels, 54% of teens reported not hearing as well, and 1 in 4 had ringing in their ears. Teen boys, more than teen girls or adults, seem to blast themselves with louder volumes for longer periods of time. So what is a cochlear implant? You may have heard that term before. It's a device for converting sounds into electrical signals and stimulating the auditory nerve through electrodes threaded into the cochlea. And how does it work? Well, it translates sounds into electrical signals that are transmitted to the cochlea and via the auditory nerve, which are then relayed to the brain. Really amazing technology. How does the brain detect loudness? A soft tone activates only the few hair cells attuned to its frequency. Given louder sounds, neighboring hair cells also respond. So the brain interprets loudness from the number of activated hair cells. What is one theory of how the brain detects pitch? Well, place theory is one, and we're going to talk about another one on the next slide. It presumes that we hear different pitches because different sound waves trigger activity at different spots along the cochlea's basilar membrane. Thus, the brain determines a sound's pitch by recognizing the specific area on the membrane that is generating the neural signal. Now, the frequency theory, which is also known as the temporal theory, is a little bit of an alternative, but they actually end up working together. The brain reads pitch by monitoring the frequency of neural impulses traveling up the auditory nerve. The whole basilar membrane vibrates with the incoming sound wave, triggering neural impulses to the brain at the same rate as the sound wave. If the sound has a frequency of 100 waves per second, then 100 pulses per second travel up that auditory nerve. How does the volley principle explain hearing higher frequency sounds? So, and I just want to clarify that both the place theory and the frequency theory sort of work together to explain high pitches versus low pitches. By firing, okay, so in terms of the volley principle, it's that we can only process sounds up to a certain pitch and frequency. So by firing in rapid succession, neurons can achieve a combined frequency above 1,000 waves per second. So like soldiers who alternate firing so that some can shoot while others reload, achieving greater combined firepower, neural cells can also alternate firing. Place theory best explains how we sense high pitches, and frequency theory, extended by the volley principle, explains how we sense low pitches. So they kind of work together, like I said. Finally, some combination of place and frequency theories likely explains how we sense pitches in that sort of intermediate range between the high and the low pitches. How do we locate sounds? And I swear some of us are much better at this than others. Sound waves strike one ear sooner and more intensely than the other. From this information, our brains compute the sound's location, although you might notice that some people, like I said, are better at being able to tell where sound's coming from than others. There are definitely some individual differences there, it seems. So let's review our learning targets. Describe the characteristics of air pressure waves that we hear as sound. Sound waves are bands of compressed and expanded air. Our ears detect these changes in air pressure and transform them into neural impulses, which the brain decodes as sounds. This is audition, which is just another fancy way of saying hearing. Sound waves can vary in amplitude, which we perceive as differing loudness, and we measure that in decibels. Sound waves can also vary in frequency, which we experience as differences in pitch. So how does the ear transform sound energy into neural messages? So the ear funnels sound to the middle ear. The inner ear consists of the cochlea, which is it consists of the cochlea, the semicircular canals, and the vestibular sacs. You can go back, you can see some of those images that we had, or there's some really great pictures in the textbook. Sound waves traveling through the auditory canal cause tiny vibrations in the eardrum. The ossicles amplify the vibrations and relay them to the fluid-filled cochlea. Rippling of the basilar membrane causes those tiny little hair cells to move, triggering neural messages to be sent to the auditory cortex in the brain. So how does the ear transform sound into neural messages? Well, this actually is telling us a little bit about how these different types of hearing loss can have an effect on us. Not can have an effect on us, what they specifically are. Sensory neural hearing loss results from damage to the cochlea's hair cells. Sorry, that's my dog in the background. It results from the damage to the cochlea's hair cells on their associated nerves. Conduction hearing loss, on the other hand, results from damage to the mechanical system that transmits sound waves to the cochlea. So cochlea implants can restore hearing for some people. So sorry about that. This is just a continuation. These two are sort of understanding the same learning target there. They have the same title. Okay. Discuss how we detect loudness, discriminate pitch, and locate sounds. So our brain interprets loudness from the number of activated hair cells. We had those two different theories, place and frequency theory. Place theory explains how we hear high-pitched sounds, and frequency theory, low-pitched sounds, and a combination of the two probably explains how we hear those intermediate range sounds. Place theory proposes that our brain interprets a pitch by decoding the place where a sound wave stimulates the cochlear's basilar membrane, whereas frequency theory proposes that the brain deciphers the frequency of the neural impulses traveling up that auditory nerve into the brain. By alternating their firing, which is called the volley principle, neural cells enable us to sense sounds with high frequencies. Sound waves strike one ear sooner and more intensely than the other, which helps us with figuring out where the sound is coming from. The brain analyzes the minute differences in the sound received by the two ears and computes the sound source. That was a lot of information. Thank you for listening, and sorry about the interruption of my two dogs. Have a wonderful day and take care. Bye-bye.